In this video, we're going to learn how to verify that a number is prime. So first we're going to define a prime number. So a prime number is a whole number greater than 1 whose factor pairs are only the number itself and 1. So remember that we saw the relationship between factors and divisibility, so let's just add another way to think of prime numbers. A prime number is a whole number greater than 1 that is only divisible by 1 and itself. And these are equivalent statements that we'll use interchangeably to solve these problems. So first, what we're going to do, notice there's the perfect squares table again, and we're going to use the same idea we used in the last video, where we found all the factors of a number by finding all the factor pairs. And then we're going to use another idea to make the process a little bit simpler for verifying prime numbers. But first let's develop the idea. So if we wanted to find, we're going to verify that this is prime, but if we wanted to find all the factor pairs of 23, remember that we'd look at the chart and see that 23 lies between 16 and 25. And then remember we round down to the smaller number, which is 4. So this would be, here it says largest prime you have to check. Let's save this for later, and right now we're just going to say largest number, because 4 isn't prime, that you have to check. So we're going to do this just like the last problem. So now let's make our list. We have 1, 2, 3, and 4. Well, we know that 1 times 23 is 23. And now we want to see if these other numbers are factors, and if they are, we'd find their corresponding factor pairs. Now you may notice that 23 is not even. It doesn't end in 0, 2, 4, 6, or 8. So it's not divisible by 2. So 2 is not a factor of 23. And you can also do the division on your calculator and see that you'll have a decimal, which means there's a remainder. So 2 is not a factor, so I'm going to cross it out. Now let's try 3. So you may think 23 divided by 3, well that goes in 7 times to get 21, but there would be a remainder of 2. Or we can divide 23 by 3. We'll see that there's a decimal, so 3 is not a factor. And finally, we'll check 4. And 23 divided by 4 is going to be 5 with a remainder, so 4 is not a factor. Now, let's just notice something, and this is a strategy you can use when finding all the factor pairs as well. I knew that 4 wasn't going to be a factor because 2 was not a factor of 23. So there's a connection here. If a number is divisible by 4, it must be also divisible by 2. And the reason for this is that 4 is divisible by 2, so if the number is divisible by 4, it will also be divisible by 2. Let's just look at a really small example. So let's make the number 12. So there are 12 dots. It's divisible by 4. So I made 3 groups of 4. And notice, since 4 is divisible by 2, each of those groups of 4 can be broken into groups of 2. So 12 would also be divisible by 2. Okay. Just note this doesn't work in the other direction. So I can't say if a number is divisible by 2, it's divisible by 4. So for example, the number 6 is divisible by 2. There are 3 groups of 2. But it's not divisible by 4. For 4s, it would have 1 group of 4 with 2 left over. So what this means is we actually don't need to check 4 when we're checking to see if this number is prime or not, because we would have already checked 2, and if it was divisible by 4, it would have had to be divisible by 2. So this is going to take us to a way of shortening this process. Notice here there's a table of prime perfect squares. And we're going to use this idea to say, well, if we're just checking to see if a number is prime or composite, we only have to check to see if it's divisible by any prime numbers whose square is less than the number given. So this is our rule for this one. So divisible by any prime numbers whose square is less than the number given. And you'll see here 4 isn't included because if it was divisible by 4, it'd be divisible by 2. 6 is not a prime. It has the factors 2 and 3. Well, if it was divisible by 6, it would have been divisible by 2 or 3, and etc. 9, 10, 12, etc. So to test for what we sometimes call primality, if a number is prime, we're just going to use this process. So originally this said largest prime number, and in this case, if we use the prime number perfect square chart instead, notice 23 lies between 9 and 25, and when we use the smaller number, we would only have to check up to 3. Okay. So this is going to reduce our work a lot. We're going to have to check to see if the number is divisible by a lot less number than if we were finding factor pairs. So notice it wasn't divisible by these numbers, so we verified that it's prime. This was prime because it's not divisible by any of these factors. Let's do a couple more. So 89, let's see where it lies in the chart. Well, it's bigger than 49 and it's less than 121. And we will use the smaller number, so 7. So we have to check, the largest prime we have to check to see if this is divisible by is 7. And notice the primes less than that are just 2, 3, 5, and 7. Okay? We don't have to check 1. Every number is divisible by itself, and prime numbers, therefore, too, are divisible by themselves. So now we can go through this process. So is 89 divisible by 2, or is 2 a factor? Well, it's not even, and if you're not convinced, divide on your calculator. Is 89 divisible by 3? Well, let's divide. And notice there's a decimal, which means there'd be a corresponding remainder. So it's not divisible by 3. Is it divisible by 5? Well, there's a quick check for 5. Numbers that are divisible by 5 end in 0 or 5. So you may remember counting by 5s when you were younger, 5, 10, 15, 20. So this does not end in a 5, so we don't even really have to check that, but you could verify it on your calculator if you want. And lastly, let's check 7. And notice we get a remainder again. So that means, since 89 is not divisible by any of these numbers, we have verified that it is prime. Okay. So now let's look at 163. So 163 lies between 121 and 169, and we go to the smaller number of 11. So notice this means we only have to check to see if it's divisible by 2, 3, 5, 7, and 11, which is really not a lot of numbers to have to check. Okay. Well, it's not even, so it's not divisible by 2. Now let's check 3. 163 divided by 3. Well, there's a remainder, so it's not divisible by 3. It's not divisible by 5 because it doesn't end in 0 or 5. Now let's check 7 and 11 on the calculator. 163 divided by 7. It is not divisible by 7. And finally, we'll check 11. Oh, 163 divided by 11. And again, there's a remainder because I see that there's a decimal there. So we have verified that this is prime.